2, 1. Welcome to the Consulting Specifying Engineer webcast, How to Design Electrical Systems to Reduce Arc Flash Incident Energy, sponsored by Schneider Electric. I'm your moderator, Amara Razgas, and I'm happy to join you on behalf of Consulting Specifying Engineer and CFE Media. Here are some tips for today's webcast. If you're having trouble with your slides or sound, refresh your browser or click the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your computer. If you are having technical problems, please click on the question mark at the top right corner of your screen to bring up a list of system checks to try before contacting an online technician. If you do need a technician, type a message into the Ask a Question box, and someone will respond as soon as possible in the Answered Questions box. Type questions for today's expert presenters in the Ask a Question box on the left side of your screen. The Q&A portion will start after the prepared presentation, so that means it will begin in about 45 minutes. Today's webcast is being recorded, and you'll receive an email with the link to the archive in about a week. To download these presentation slides, use the Event Resources on the left side of your screen. I'm happy to introduce today's presenters. Erhan Kokal received a Master of Science in Engineering from METU, and while there, his thesis on computer vision-based mobile robot navigation was published. He joined Schneider Electric Turkey as an R&D engineering, designing the testing arc-resistant medium-voltage switchgear. He currently works with Schneider Electric, Square D, as an offer marketing leader for low-voltage power distribution systems. Dakota Blair earned a Bachelor of Science degree in Business Communications and a minor in Mass Communication from Middle Tennessee State University. Blair has 10 years of industry experience working in the energy management and electrical distribution field, holding positions as marketing manager, hydronic sales engineer, sales application engineer, and most recently as a global offer manager for low-voltage motor control centers. Blair is currently an EcoStruxure Power Business Development Specialist at Schneider Electric. Rod West is a Senior Staff Engineer for Schneider Electric. He holds a Bachelor of Science degree from Rose-Hulman Institute of Technology. He has worked in the electrical industry for more than 28 years and holds 11 patents for various types of electrical equipment and components. He represents NEMA on CMP 8 for the National Electrical Code and is a Principal Technical Committee member for NFPA 70E, the standard for the electrical safety in the workplace. Tim Faber graduated from the University of Wisconsin-Platteville with a Bachelor of Science in Mechanical Engineering. He has 30 years of experience with Schneider Electric as a circuit breaker engineer working on development of low-voltage circuit breakers, power connectors, and switchgear, and is currently working as an engineering fellow in low-voltage advanced equipment. Timothy is a member of IEEE and holds more than 20 U.S. and European patents. Thank you for joining us today, gentlemen. Erhan, let's get started.
Thank you. Arc flash incidents can happen. It can happen anytime to anyone who is working with energized equipment. The results can be costly and tragic, with damaged equipment and personal injuries. There are several arc flash incident energy mitigation solutions available. The questions then become, what are the suitable methods for your system? And how can we minimize the risk of hazard at its source in an economical way? Dr. Parsons Anthony Parsons raised a great question during IEEE Electrical Safety Workshop in a few months ago, addressing what is the sufficient isolation in between line side and load side of an electrical enclosure. IEEE 1584 recommends using an upstream device for calculations if the line side isolation is questionable. This situation requires engineering judgment or having a certification from the manufacturer in order to decide whether your main breaker is sufficiently isolated. Otherwise, study engineers should label the equipment based on the worst case scenario. We will address all these concerns in this presentation with a new technology called ArcBlok. ArcBlok also aligns with NFPA 70E risk control methods. So first, Rod will talk about codes and standards perspective. Rod?
Yes, thank you, Orhan. So first, I would like to briefly lay some groundwork by discussing the risks that electrical contractors and other electrical workers face daily. Most of us know that there are two primary electrical hazards. The first one is shock. And shock occurs when electric current passes through the body. It can occur in varying levels of intensity, duration, and path. And electrocution is a shock that results in a fatality. We've been aware of shock hazards for over a century. Many years ago, this drove changes in installation requirements and product designs, including changes such as enclosing the open style switches and busing that were the norm in the early to mid 1900s. Unfortunately, electric shock is relatively common. According to NFPA 70E Annex K, there are approximately 30,000 non-fatal shock accidents per year. While that may be what is documented, I believe that number is far too low, because nearly everyone I know has experienced an electrical shock at one time or another, and many of us have been shocked more than once. So I wouldn't be surprised to find out that number is actually 1 or 2 orders of magnitude higher. In most cases, shock is a result of inadvertent contact with energized parts, either via direct touch or while using a conductive tool. And several solutions are available to mitigate shock hazards. Depending on the situation, designers use distance, they use insulation or barriers, and the barriers could either be permanent or temporary. The other electrical hazard is arc flash. And an arc flash occurs when current passes through ionized air or a plasma. And here again, there are varying levels of intensity and duration for an arc flash event. Thankfully, arc flash events are less common, but even so, they do occur. And the burns that result from an arc flash event are often devastating. And this is because the temperature of the plasma can be extremely high, up to 35,000 degrees Fahrenheit. Unlike shock, contact is not required for an arc flash event. An arc flash can injure or even kill at distances of 3 feet, 10 feet, or even more. So, our recognition of arc flash hazards is much newer. The concept of arc flash didn't even appear in safety standards like 70E until 1995. So there's another related hazard called arc blast, and that's the explosive effect that results during an arc flash event. And it's caused by the rapid expansion of superheated air and other materials. Arc blast appears to be a function of containment and fault current and some other factors, but it's a secondary hazard, and it's the result of the primary hazard, which is arc flash. So, it's critical that qualified workers be able to identify the hazards and protect themselves from the risks that result from both types of hazards, shock and arc flash. And the 70E standard requires workers to reduce risk using a hierarchy of risk control methods. So As you can see on the graphic here, there are 6 types of risk control methods. The methods are arranged in order from more effective at the top to less effective at the bottom. Those that appear at the top of the list are called higher order controls. At the very top of this list is elimination. And in the context of 70E, elimination is accomplished by establishing an electrically safe work condition. Most of you know that an electrically safe work condition is a state in which the circuit parts have been disconnected from their source, locked and tagged in accordance with the established standards, and then tested to verify the absence of voltage. Now, it's important to understand that an electrically safe work condition, it's a temporary state, and it exists only for that period of time for which the electrical hazard is eliminated. Also in that top half of the list, you're going to find engineering controls. And these include options that reduce risk without worker involvement. An example of an engineering control that automatically reduces risk of shock, for instance, would be GFCI protection. Another would be the use of barriers to prevent inadvertent contact. Now, these higher order controls are more effective. They're usually applied at the source, and they're less likely to be affected by human error. The solution you're going to hear about later in this presentation is a higher order control. It's an engineering control that's integrated into the equipment. It can also be used in conjunction with other control methods to establish and maintain an electrically safe work condition. Now, the lower order controls appear at the bottom of the list, and these include awareness, administrative controls, and finally at the bottom, PPE. These methods are often used in conjunction with other methods to lower the overall risk level. Examples include alerting techniques such as signs or hazard labels, temporary barricades that are placed around the work area. And then the final line of defense is PPE. PPE, which stands for personal protective equipment, must be available when it's needed. And it needs to be properly rated for the hazard, whether that hazard is shock or arc flash or both. Okay, so I just mentioned that lower order controls are less effective, and this is because they're usually not applied at the source, and they're more likely to be affected by human error. Here you can see that research indicates that most electrical accidents are the result of human error. You can also see that the most recent data indicates that in 2017, there were 134 fatalities in the U.S. due to electrical incidents. In other words, a fatality related to electricity occurred in the U.S. nearly 3 times a week. And that's just an overwhelming statistically, but thankfully the rate is decreasing. The rate was nearly double that just 20 years ago. Human error when working around energized equipment can expose workers to both shock and arc flash hazards. And in this short video that we're going to play, you can see the effects of an arc flash event inside equipment that is not designed to contain or manage an arcing event. Let's watch that video together now. Okay, so clearly the equipment in that video was damaged, and likely it will need either extensive repairs or replacement before it can be returned to service. Even more concerning would be the effect that would have on a person working on or near the equipment. Before the video, I mentioned that although the rate of injuries and fatalities is still too high, it is declining. So why is that? And I'd suggest that it's due to a number of reasons. First off, a raised awareness of arc flash hazards, but also superior PPE and improvements in equipment designs, improvements in work practices, and the evolution of codes and standards. So let's take a look at just a couple of codes and standards examples. So on this slide, we all know that the current NEC is the 2017 edition. In it, you will find installation requirements related to barriers and certain types of gear. And specifically in 408.3, you'll find requirements for barriers in service panel boards and switchboards and switch gear. But did you know that that requirement will be expanding in the next edition of the NEC? So the 2020 NEC, which will be available about 1 month from today, will have a new requirement. And here's a sneak peek at one of the changes you can expect to find in the next edition of the code. This is a new requirement in Article 230 that refers to all service equipment instead of being limited to just panel boards, switchboards, and switchgear. And you can see that the requirement is focused on inadvertent contact, which is generally associated with limiting exposure to shock hazards. This is a good addition. However, while a barrier may be effective at protecting against shock hazards, unless it's been evaluated for arc flash protection, it should not be considered to provide protection during an arcing event. And the solution you're going to hear about in a few minutes will satisfy this new barrier requirement, plus it will address the line side arc flash hazard as well. Okay, so on the previous slide from the NEC, it was from the National Electric Code, and we know that the NEC covers installation requirements. Another standard that's widely used in industry is NFPA 70E. And 70E is the standard for electrical safety in the workplace. NFPA 70E does not cover installation requirements. Instead, it provides information to help protect employees. Following 70E helps employers comply with federal regulations such as OSHA 1910 and 1926. Now, the present edition of 70E is the 2018, and this edition will be superseded by the 2021 edition in a little over a year from now. So again, the 2021 edition is not yet complete, but here's an example of new language that will likely be added to informative Annex O of the 70E standard. Now, Annex O deals with safety-related design concepts, things that facility owners, facility managers, employers should consider when designing an electrical installation. The new language will add energy-reducing line-side isolation to the list of incident energy reduction methods. It will describe equipment that encloses the line-side conductors and circuit parts and has been evaluated to provide both shock and arc flash protection from events on the line side of a circuit breaker or switch. So now I'll turn it over to Tim Faber, who can explain more about this type of approach.
Thank you, Rod. So we've heard from Rod about the general risk environment and the code and standards development. And I'd like to talk to you a little bit more about this specific topic today and a little bit more nuts and bolts about what it is and how it works. Let's start with, on the left side of your screen, let's start with a one line of 1,000 kVA 40 volt system, including the main transformer and downstream switchboard. In addition to the one line diagram, it's been color coded with incident energy levels calculated per IEEE 1584, corresponding to roughly the line side of the main circuit breaker and the load side circuit breaker. In this case, the incident energies are 15.6 calories per centimeter squared in zone 1 and 1.6 calories per centimeter squared in zone 2. The difference is essentially the difference between the clearing time of the 65 kA fuse and the 1200 amp main. So we can see, and is generally the case, that the risk environment is not uniform and the risks are on the line side of the incoming breaker, as demonstrated in the one line and in the equipment image, are generally higher. It's also true, as Rod has mentioned, that the separation, the integrity of the barrier between the zone 1 to zone 2 energies is not something that's often distinct or reliable. The solution that we will talk to you about today is targeted directly at the Zone 1 environment on the line side of the breaker. This solution is created by building what is essentially a miniature arc-resistant enclosure in which special features have been added to make it exceptionally good at arc management, both in how it treats the arc directly and how it handles its byproducts. So let's take a look inside and see a little bit more about this. So looking under the hood, we can see the recipe for, on this slide, says line side arc insulation module, which is another word for ArcBlok. And we can see it revealed in 3 steps. On the left here, what we see is the arc-resistant shell, as in the previous slide. And this is there to ensure that whatever arc byproducts are generated, that they are kept reliably maintained. We don't know how to completely prevent arcs or completely extinguish them in 0 time, so we have to make sure that whatever we do generate stays inside. If we remove the pressure cover and look inside, we see the cable vault in the center image showing the incoming power cables and the thermoset polyester power connector surrounds. These are designed to maintain a maximum degree of separation between the power connectors, both phase to phase and phase to ground. They effectively emulate an IEC arc-free design, which reduces the chance that an arc can be generated in the first place. However, going further than IEC arc-free design, this design is performance tested per C3720.7 and is also reliably self-clearing. And we'll talk about that in a little more detail about how it works in the next slide. But let me just say as a comment, we didn't start out to make this arc clearing. We started out to build a very good arc-resistant enclosure. But as circuit breaker designers, arc management is kind of our thing. And we said, well, if we can manage the arc in a breaker, we maybe can manage one in the power connector area as well. And we got pretty excited when we realized that that's actually the case. And so let's talk a little bit more about how that works. So as it turns out, we can reliably clear an arc like a circuit breaker, but it takes us a few milliseconds to do so. This is because, like a circuit breaker, the design is intended to starve the arc of heat so that it dies of a cold as it approaches our forced current 0. During the arc period, we control where the arc can go, ensure that its length and therefore its arcing voltage is maintained, and we cool it by adding generous amounts of ablatives we evacuate the excess energy out the top in the exhaust. So basically we emulate what a circuit breaker does, but with no moving parts. As it turns out, our colleagues at Telemecanique many years ago had the same idea with what they called a slide fiber interrupter that uses thermoset polyester barriers to control the arc as opposed to the more classic arc stacks. So even though we can interrupt the arc quickly, less than 1 cycle, there's still energy in that 1 cycle inside the ArcBlok. On the circuits we're talking about, 40 volts, 100K, it's going to be on the order of 4 calories per centimeter squared. And we need to make sure that it stays separate from the user. So to do this, we've added some more features to the ArcBlok shell. So borrowing ideas from our PZ4 arc-resistant switchgear and our explosion-proof switches, we added what we called overlap seals to any leakage paths. We didn't believe that we could build a gas enclosure. We didn't believe that was practically possible to build or maintain. So we built an energy type one as well. And what this means is that the leakage paths are designed so that any plasma that comes out is squeezed and cooled to below the restrike temperature. And this is to avoid that an arc could be transferred out of the ArcBlok itself and then reignite somewhere else in the cure. And as much as we don't want the arc to get out, we also don't want one to get in either. Not allowing an arc to get in ensures that the load side arc cannot transfer the line side, and it addresses directly the question of separation of zone 1 and zone 2. And in many cases, like in this example, that would mean a 10 times increase in incident energy. With ArcBlok, the overlap seals the chance that a viable arc could enter the module is very, very small. And then even if it did, it would be immediately cleared, effectively a belt and suspenders approach. In terms of protecting the user, the cooling effect of the overlap seals, the limit duration of the arc, typically less than 1 cycle, the evacuation of energy via the exhaust, that these all combine so that the incident energies in the immediate proximity of the user, if there was to be an arc inside the arc block, tend to be very low, much less than 1 calorie per centimeter squared. This means you can effectively forget about the line side zone 1 incident energy risk and focus solely on the load 2 on the zone side. On the zone 2 side, which is the load side of the breaker, where other techniques like EMS, ERMS, ZSI, and relays that are available to further reduce incident energy. Lastly, the reliable isolation of the line side incident energy means that opening the main circuit breaker of the panel effectively establishes an electrically safe condition without requiring opening the next upstream device. This reduces the size of a planned outage to the piece of equipment in question and reduces the impact on the overall facility. So let's see it in action. We're going to show you an animation of what's inside the arc block, including a visualization of arc development and extinguishing. Okay, so one quick comment. You could see the arc grow with the normal current cycle, but what you couldn't see in the animation, and again, it is an animation, but it is a fairly good animation. What you couldn't see is how the ablatives and the exhaust overwhelm the arc and kill it with cooling. But now let's look at an actual lab test to get a little more into the details here. So these are oscilloscope traces of actual test results on MCC ArcBlok. Not everyone is used to looking at these, so let's take a few seconds to discuss a little bit about what they are. The traces contain voltage and current measurements taken during the arc flash testing in the library. The vertical scales are voltage and current, and the horizontal scale is time. In terms of scale, the upper traces are on the order of plus or minus 1,000 volts. The lower traces are on the order of plus or minus 60,000 amps. And the time scale is on the order of 10^1/1000 of a second and represents only a portion of the test for which there was arcing. More on this in a bit. These tests were both run at 480 volts, and the test on the left is at 111,000 amps available, and the one on the right is at 42,000 amps available. A few things to note. First is the test station was on for 150 milliseconds, more than 9 cycles. But the test durations themselves, or the arc duration themselves, were less than 10 milliseconds, less than 1 cycle. In other words, the ArcBlok device cleared the fault in less than a cycle and carried the open circuit voltage for the 8 remaining cycles, just like a circuit breaker. This is one of the most important benefits of self-clearing. We do not care what the trip settings are of the upstream device. It could be 3 cycles, 30 cycles, 3 seconds, or even longer, and the ArcBlok clearing time of less than 1 cycle always applies. The next upstream device does not even have to open. The module is designed to reliably self-clear for any valid voltage or available fault current of the breaker that it's attached to. The next thing is that the amount of let-through current is dramatically reduced. In this example, the peak let-through current of 111,000 amp test was just 46 kiloamps out of a prospective 245,000 kiloamps, representing an 80% reduction. This is because the 800 plus volts of arc is designed to emulate a current limiting circuit breaker, somewhere around very similar to about 800 amp current limiting circuit breaker. The performances of 42K are a little less impressive, but still remarkable. So let's take a look at some test videos and see what this thing looks like in the test lab itself. So we're going to show you here some test videos of a typical MCCC pre-ArcBlok. Then we'll show you the ArcBlok. And then in the third video, it'll show them side by side. Watch carefully in the third video because they both tests are simultaneous. Okay, so what you've seen there is the power of managing internal arcs in treating power conductor systems like their circuit breakers, limiting the energy and duration of any arcing fault, containing and redirecting any energy that is there away from the user, minimizing damage and downtime. And all this with the simplicity and reliability that comes from a passive design with no moving parts. So let's go back to Erhan now to show you some more about the commercial offer.
Thank you, Tim. Beginning of this project, our customer survey showed that a simple, reliable, and affordable design are the expectations from us as a manufacturer. Selection of arc flash mitigation method and the methods actually for a system, it's a challenging task for many facilities. In order to achieve this challenging task, you may ask yourself some critical questions in the early stage of the system design. For instance, for example, first of all, how can I reduce the risk? That's the most important question, right? And what's my goal? PPE2, PPE4, or mixed in my overall system? Which operations do I need a PPE? Maintenance, troubleshooting? Is service continuity or equipment damage a concern for my system and process? It is generally actually in nowadays. What's my budget to achieve the goal? Cost is important. And footprint, restriction for additional construction like exhaust plenums, etc. The answers to these questions and more will shape the system design. Our ArcBlok technology redefined the equipment construction to play an important role for personal and equipment protection. It will also make the selection of arc flash reduction methods easier for everybody, like specifiers, designers, end users. We used safety by design approach. Here are some recommendations while selecting arc flash mitigation techniques for your system to consider. First, you need to reduce arc flash incident energy level or PPE as much as possible. And you need to improve your service continuity. You may use some other techniques, but if your equipment is damaged, it may cause a service continuity problem. You need to reduce exposure to live parts as much as possible. This is the principle of safety by design. And you need to simplify. This is very important, actually. You need to simplify commissioning and usage to reduce human risk factor. And we need to optimize cost, of course, for CapEx and OpEx, operational cost. Of course, save space with the minimum footprint and less construction. Tim explained the technology in detail, right? But what about in system level? What does ArcBlok do? ArcBlok blind site isolation technology is a passive system, right? Many available solutions focus on actively removing the arcing fault after it begins on the load side. On the other hand, ArcBlok technology reduces the likelihood of an arc flash incident on the line side, which is usually the worst case scenario from the arc flash calculations due to upstream protective device. However, arc flash incidents still can happen. We all accept that, right? For example, humidity and environmental conditions may be one of the root causes. So if it happens, this innovative technology also reduces the arc flash incident energy levels significantly. It's around 1.2 calories per centimeter square. In other words, it's a system to minimize the human risk factor and reduces the arc flash incident energy level. Here are the technical features of Square D Model 6 MCC available now. It's up to 1200 amp and will be expanded to higher amperages in 2020. It's available for up to 100 kA withstand current at 480 volt. It is tested per NC and IEEE standard and UL witnessed. It's the standard footprint. In other words, this ArcBlok edition will keep the same small footprint with standard Square D Model 6 MCC. Here is the IEEE research graph showing the source of the equipment in the distribution system causing injuries. As you can see, MCCs is the second highest source of the incidents. In the field, operators are more engaged with MCC than any other low voltage distribution equipment. For that reason, we started our design with Model 6 MCC, but this new innovative technology will be expanded for switchboard, panel board, etc. PPE is an important part of a safety program. We all accept that. But as a last line of defense, like Rod explained, it should be as comfortable as possible for efficient work practices. Therefore, engineering controls with product design will help reduce the magnitude of the hazard to the worker. Considering this fact, in addition to ArcBlok main feature, we added some augmented engineering control features to ArcBlok system. Now, my colleague Dakota will talk about these supporting features and benefits of ArcBlok. Dakota?
Thank you, Erhan, and thank you, everyone, for being here today. So for the next few minutes, I'm going to show two innovative features that are included with the ArcBlok solution, followed by the conclusion and the start of our Q&A. So, first one that I want to talk about has to do with the thermal monitoring. One of the challenges that our team faced when developing the ArcBlok solution was how can we help our customers easily gain access to important thermal data on connection points that are located within the ArcBlok vault itself. Luckily, now sensor technology as a whole has evolved and continues to mature, whether it's in our vehicles or our homes and now our electrical equipment. Traditional collection methods have evolved. Periodic tests that only happen and occur periodically throughout the year, using handheld IR scanners to thermography cameras. Now, with new technology, we can offer continuous communicating self-powered sensors that can be collected from your mobile device. So that eliminates being exposed to any kind of live parts. So let's talk a little bit about what I'm talking about here. And I'll introduce you to one of our newest offers called the EaserG TH110. The EaserG TH110 is a part of Schneider Electric's family of EcoStruxure Power connected components. And it's a brand new innovative feature that comes included with the ArcBlok solution. This is a good picture here, and we'll start the video. Show you where the sensors are. Get the data on our phones and collect it from a safe distance. There's one sensor per phase, as you can see. They are self-powered using the bus connections and the ribbon. Innovative solution that's attached to the back of the sensors. It being self-powered eliminates the need to replace batteries, have to go into the ArcBlok periodically. And they're all equipped with wireless Zigbee communications, which makes the thermal readings available on our free Thermal Connect app. So you would use your phone to collect the data instead of the traditional method. So it provides a more quick, convenient way to view the temperature data in a way that minimizes exposure to live parts, and it helps personnel be outside of the arc flash boundary area. This is our EaserG TH110 sensors that come with the ArcBlok solution. So now we'll move on to the second innovative feature included with the ArcBlok solution, and that's called the AVT for short, Absence of Voltage Tester. And you can see a good picture of it here. So Absence of Voltage Tester is one of our brand new launches. It's very innovative. It's an evolution in a traditional test procedure that's laid out in NFPA 70E Article 120.5 that explains establishing a de-energized work condition using a traditional handheld meter method and steps that are required to follow. The AVT is actually written in the new Article 2018 and is actually the only acceptable method permitted in place of a traditional handheld method. And how it works is it takes all of the processes that you would use a traditional meter, a little handheld meter, to test each phase, to test continuity, to test phase to phase, phase to ground, and automates it for you. So it takes a procedure that could usually take around 30 minutes to an hour depending on the application. It requires, again, depending on the application, people to put on extra PPE and be possibly exposed to live parts, and it automates it all and allows you to do it within a push of the button in about 3 seconds. The AVT runs through the test functions in sequence. It tests continuity, voltage, phase to phase on each phase, and phase to ground, and it gives you an indicator telling you that you are working on it in a safe work, the energized work. This is one of our newest offers that is included with the ArcBlok solution, and this should drastically help you cut down on time-consuming activity that requires you to go trace down things upstream, all with a push of the button in a very SIL 3 rated device. That meaning it's very intuitive and easy to use. It gives you a green light and a red light. It's very easy to understand. That's the second feature I wanted to talk to you about. It's called the absence of voltage tester. So that's been a lot of innovative information to digest. So in conclusion, I want to take some time to go over just some of the important bullets that you've heard today, just to reiterate. One being ArcBlok solution reduces the chance of an arc occurring. 2, it acts like a virtual circuit breaker. 3, independent next upstream device settings. 4, it allows for the possibility of a no outage internal arcing event, which we did state, you, Tim, and Erhan both touched on. Number 5, it is reliable. And reliability is one of our most unique and powerful value propositions for the ArcBlok feature. It's reliability and kind of set it and forget it type passive construction is something that we know that our customers have been asking for. So we're excited to be able to bring that. 6 is it eliminates the needs for exhaust plenums. 7, and the last one is it can help simplify arc flash analysis and assessments and labeling to try to cut down on the complexity and help simplify the ordering process and the installation and the labeling process. So those are the points we want to try to reiterate, and then now what we're going to do is move into Q&A, where all the presenters will have an open floor and be able to present. I do want to end the entire presentation with one last video that just, again, reiterates everything that we've done here today and everything we've talked about in a short video, and then we'll move into
An arc flash is a serious concern in electrical equipment. It is an extremely dangerous and life-threatening event. To address this, the National Fire Protection Association has implemented arc flash protection standards in NFPA 70E and the National Electrical Code in Section 240.87. These standards define work practices to safeguard employees from injury while exposed to electrical hazards. But the fundamental challenge remains. What more can be done to move arc flash mitigation from work practices to engineering controls, thereby reducing the likelihood of occurrence or the severity of an arc flash? You can look to Schneider Electric, manufacturer of the Square D brand of electrical distribution equipment, for the latest innovative solutions. The new patented Square D ArcBlok technology within our motor control centers brings a new level of performance to arc flash mitigation. This passive system provides arc isolation for the most dangerous area in any lineup, the line side conductors. Arcs are less likely to occur, and if they do, they are contained inside the cable vault, providing incident energy low enough to wear comfortable PPE without the bulky suits normally required. In addition, with the arc flash energy isolated and quickly extinguished, equipment damage is limited, reduced, and minimized, allowing continuity of power, and for inspection and cleaning to be scheduled at a convenient time. There should be no reason to replace the main section. Another feature of the ArcBlok motor control centers is wireless thermal sensors. These sensors continuously monitor the temperature of the line terminals, making it unnecessary to perform infrared thermography in this area, and thus avoid exposure to the line conductors. It can be easily read on your smartphone using our app and dongle while standing outside the arc flash boundary. Just scan the NFC tag on the equipment, open the app, and our wireless feed will update your screen to obtain the latest temperature data from your equipment while you remain safely beyond the arc flash boundary. Whether you are updating your existing MCC or buying a new one, get a new level of arc flash protection with ArcBlok technology from Square D by Schneider Electric.
All right, excellent. Thank you to our Schneider Electric experts for their presentation. And now our presenters will answer questions about this topic. Please type your questions in the Ask a Question box on your screen. You can type the presenter's name ahead of the question so that I know who should answer that question, and we will get to as many questions as time allows. Additional information will be posted online at www.csemag.com, that's csemag.com, with the archived version of this webcast. And I am actually going to answer the very first question. Can you download this? Yes, you may download the presentation slides using the event resources on the left side of your screen. And if you would like to watch all the videos again, they will all be available with the on-demand version of this webcast. You'll get an email in about a week when that on-demand version is available, and you may watch this once more. All right, we're going to take our very first question here. Erhan, I'm going to kick this to you, and then you can determine how to best address it.
Sure.
How does ArcBlok compare to installing arc-resistant gear?
I think this is a great question. It's because of the fact that I heard that question many times. Both of them, first of all, the common features, they are passive, right? And the difference between ArcBlok and ArcRes, ArcBlok is also mitigating the arc flash incident energy levels significantly. It's acting like an active arc flash mitigation system and combining all those features we are using in the arc-resistant system. Let's imagine you have an arc-resistant equipment with plenum and you are exposed to energized part. You are in danger because arc-resistant system is containing the arc inside of enclosure. However, with ArcBlok, we are mitigating the arc flash incident energy levels significantly, and we are protecting both equipment and the personnel. I hope this will answer the difference.
Our next question is, how difficult is it to add ArcBlok to an existing Square D MCC? So talk about another manufacturer. If you added it to another product,
yes,
how would that work?
That's a very, very good question. It's actually one of our users came with that solution to us. We haven't thought at the beginning. It's a great pragmatic thinking from our customers. Yes, we can install ArcBlok for Square D Model 6 MCC installed base applications and the Model 5 as well. For the other manufacturers lineup, if they are planning to modernize, they can use ArcBlok main section as a virtual main. So they can feed their existing lineup through Model 6 ArcBlok main section. This will provide them to mitigate arc flash incident energy level on the line side, which is probably a good application for service entrance applications. That's the way to use for the other manufacturers' applications.
Okay, very good. The next question addresses reliability. Can you talk a little bit about reliability, please?
That's a huge discussion subject. Reliability is a philosophy. First of all, it's you need to consider reliability as of what's causing a problem. According to Rod's presentation, I believe he mentioned about 80% of the incidents, they are due to us, human errors. Reliability with your car, reliability with your electrical equipment, there are some mission problems, but 80% This is the statistics, right? So what we are doing with ArcBlok to mitigate the human risk factor as much as possible. What's the human risk factor for the electrical equipment? Get exposed to energized part, right? So what we are doing with ArcBlok augmented features that Dakota explained perfectly, we are adding some new technological advances, like temperature sensors, like absence of voltage testers. So we are trying to minimize the human factor. So that's the portion of reliability. And the second part with ArcBlok, that's very important based on my experience. If you are letting your employees to adjust something, it's because of frustration, fatigue, mainly sometimes experienced employees, like because of complacency, they are doing mistakes. So with ArcBlok system, we are addressing all those issues and trying to increase reliability factor.
All right, sounds good. Let us take the next question here. We do have a lot of questions. If you have a question, please type it into the Ask a Question box. And questions that we don't get to today will be answered online by our Schneider Electric experts. So our next question is, how many arc flashes are these devices able to withstand?
Wow, this is a really good question, actually. We have a story related with this subject. We don't have time to talk, but this system is UL witnessed and NCI EEE type test performed in our Cedar Rapids, Iowa laboratory. So the ArcBlok system, after having the first incident, is just clearing the arc such fast, so there is no any damage on the valve section that Tim explained. So you may continue to service. You can continue to energize and continue to service with the equipment. And of course, you may need to some cleaning and small maintenance, but in the testing process, we tested over 6 times and it was still continuing. So it's a huge innovative approach for arc flash incident energy mitigation because of this feature.
Okay, sounds good. And we have time for only one more question. And this question is, how much is the maximum arc time? Can you give us some information on that, please?
Sure. It's less than 1 cycle. We tested many equipment. We can say less than 1 cycle. It's sometimes 5 milliseconds, sometimes 16 milliseconds. But it's in between 5 to 16 milliseconds, we can say.
All right, awesome. Well, thank you. And thank you to our audience for those great questions. And thanks again to our speakers, Erhan Kokol, Dakota Blair, Rod West, and Tim Faber for sharing their time and expertise. I'd also like to extend a special thanks to our sponsor, Schneider Electric, for sponsoring today's event. Now that we are just about done, we want to hear how we did. An exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we use this information to improve future webcasts. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media, I'd like to thank you for attending. This now concludes our webcast. Thank you and goodbye.